Hi everyone. For exponential functions or the process of exponentiation, one of the most popular examples is the use of compound interest. So what is compound interest? Just by the word, it means it's interest that compounds on itself. So for example, if you deposit $100 and you are paid $10 per 10% per year interest, right? Then after 1 year, you will have $100 plus 10% of $100. 10% is zero point 0.1, which becomes $110. After 2 years, however, now instead of getting your interest paid on your original amount of 100, you will get an interest on your new amount of 110. So it's going to be zero point 0.1 times 110, which is now $11 instead of 10. So this becomes 121. After 3 years, now you get the interest on the 121. So now your interest is 12.1, right? So you get $133.1. So the way compound interest works is every time the interest that you earn is going to increase, right? Because you're now earning interest on a larger sum than you did before. So that's the basic idea of a compound interest. And you can see that in order to figure out how to get from 100 to 1331, you just have to keep multiplying by a factor of 1.1. What you're saying is you have 100, right? In 1 year, it becomes multiplied by 1.1. So it becomes 110. In 2 years, it gets multiplied by 1.1 again. So it's 110 times 1.1. In 3 years, similarly, it gets multiplied by 1.1 again. So it's 110 times 1.1 times 1.1. So what you notice here is that if you start with 100, these numbers are 100 times 1.1. Then you have 100 times 1.1 times 1.1. And then 100 times 1.1 times 1.1 times 1.1. So this 1.1 is the part that brings in the exponentiation, because each year you're multiplying by the same factor, which is more easily represented by just saying that each year it is the exponent increases by 1. So in general, we have this particular formula for finding the amount. So let's see what these terms mean. Suppose P is the money you deposit. That's called the principal. That's what you deposit. And A is the amount after T years, and you let it stay for T years. This is what you receive after T years. And R is the interest rate per year. N is the number of times interest is compounded per year, and T is the number of years. Now this N is kind of new. Okay. Now there are various options you have in at which, so this compounding, right? This process of changing your amount on which your interest applies, um, it's a discrete process, meaning it happens at one instant, right? So that instant needs to be chosen. Now there are multiple ways in which this can be done, right? One way is to say that we apply it once every year, or we apply it twice every year. So that would be semi-annually, or we apply it 4 times, or we apply it every month. So depending on what kind of compounding is offered, you would have different kinds of amounts. Let's look at an example. A sum of $1,000 is invested at 12% per year. Find the amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, daily. Okay, so first let's set up what is different in all of these, right? Or what is same in all of these? Let's start with that. Principal is $1,000. The rate of interest is 12%, which is 0.12. T is 3 years. What varies is n, right? So we have annual, semi-annual, quarterly, monthly, and daily. So annually would mean n is 1. Semi-annually would be 2 because there are 2 semi-annuals. Quarters, there are 4 quarters. Months, there are 12 months. And days, there are 365 days. Okay. So we have amount. This is annual, would be 1,000, 1 plus 0.12 over 1 to the power 3 times 1. Semi-annually, 1,000, 1 plus 0.12 divided by n, which is 2, over 2 times 3. Quarterly, this would be 1,000, 1 plus 0.12 divided by 4 times 4 times 3. Sorry, this should be 2 here. What else do we have? We have monthly, 1,000, 1 plus 0.12 over 12, but 12 times 3. And daily, 1,000, 1 plus 0.12, 365 to the 365 times 3. Now, what you notice here is that each time you change the way you compound, your rates are getting lower, right? This number is becoming smaller and smaller and smaller. But then the exponent is increasing. So it's a very interesting problem because it's asking you, well, if I keep on decreasing the value I'm adding to 1 and at the same time keep on increasing the exponent, what is going to happen? Are the values going to get smaller? Are they going to get larger? Do they get fixed at a point? What happens? Okay, using your calculator, try and find all of these. You can pause the video and try to fill this in and see if you notice a pattern. And then I will fill out the answers here. Okay, so when you plug in these values, you should notice that they increase ever so slightly. I mean, the difference between annual and daily is about $29, but they still increase. So, I mean, that's an interesting observation that I mean, decreasing this number and then increasing the power and they eventually sort of increase. So this brings us to this question. The question is, well, what is really happening here? This is kind of a situation of this form. And we're saying n is increasing, right? Which is where this number called e comes in. Okay, so what if this compounding is done every hour or every minute or second, right? So if it's every hour, then you would multiply this by 24 and multiply this by 24. So the structure that we're trying to look at here is 1 plus 1 over n to the power n as n increases. And this is an interesting structure because as n increases, this becomes small. So this is 1.00 something. But over here, this is a huge number, like 100,000 something. So the question is, well, does it go to infinity? Does it go to 1? And it does neither. It settles at an irrational number, e, which is about 2.718218, so on. And because it happens due to this natural process of compounding, we call this the natural exponential function when we use if the base is e. So e is just 2.718, which means if you were to plot this function, it would look like just an old exponential function. Okay, so nothing special about it in that sense. What is special is just the number e. Is that it's another irrational number like pi, and it occurs in nature. So that means we can go ahead and do these sketches because this is basically just transformations. I start with the graph of e to the x, and replacing x by negative x means I reflect it along the y-axis. Okay, and then you can also observe what is e to the negative x. That's 1 over e to the x. So whenever e to the x is increasing, e to the negative x will decrease. And when e to the x is decreasing, e to the negative x will increase. What about this next one here? This next one here, I go from e to the x to e to the 0.5x and then to 3e to the 0.5x. Now this is an example of scaling. And since this is scaling, what we are scaling here is the x-axis and then the y-axis. So really, you can actually just draw this graph directly, and the only thing you're going to change is when x is 0, this is going to be 3 instead of 1. So you kind of stretch it horizontal and you stretch it vertical. And the horizontal stretch doesn't do much, but the vertical stretch increases the point of intersection or the y-intercept to 0 comma 3 instead of 0 comma 1. Um, okay, that's it for this video. Next video we will look at some applications involving the use of e and the natural exponential function. Okay, thank you.